Here we have a wave equation, and because wave equation has two derivatives in t, it's a second order differential equation in t, and therefore it requires two initial conditions. So that's why you're given these two. And you can solve this by the usual separation of variables, where you assume that u is a product of a function of x and then function of time. And then you plug it into here and you look for solutions that satisfy both the first two. And the result is that you get answers like these. And because you can have all different kinds of n, you take the all of the solutions and take the linear combinations or the superposition of all possible solutions, which ends up being an infinite series like this. So in this question, we assume that that part is already done. And now what we need to do is to be able to match the two initial conditions, which will in turn tell you what this an is and what this bn is. So that's this question. Okay, find an and bn that satisfies the given initial conditions. All right, since ux0 is given here, let's see what happens when we plug in t equals to 0. The result is that in here you have ux0 equal to the sum of n equals to 1 to infinity, and because you're plugging in 0 into t, you get cosine 0 and sine 0, and remember cosine 0 is 1, so you're going to get an times 1, whereas sine 0 is 0, so you just get bn times 0, and then you have sine of n pi over lx. Okay, this simplifies to what? This simplifies to sigma n from 1 through infinity of an sine n pi over lx, and this tells us that what you're really trying to do is to get the ux0, represent this function here as sum of the sines. How do you do that? Well, there's a perfect method for that, which is called a Fourier series, but here, because you want it to be sine only, you really want Fourier sine series. So let's recall the formula for Fourier sine series. Fourier sine series says bn is equal to 2 over L integral from 0 to L of f of x sine n pi over Lx dx. That's the Fourier sine series, right? And in our context, because an is taking the role of bn, we can say that an is now 2 over L integral from 0 to L of f of x is either 0 or 1. So actually what happens is that from 0 to L over 2, you need to use 0 times sine n pi over Lx dx, whereas from L over 2 to L, and 1 times sine n pi over Lx dx, and because the first one is just 0, what this question is saying is you only need to integrate from L over 2 to L of sine n pi over Lx dx. Now this is just the integral of sine, so it's simply the integral of sine is negative cosine, so there's no integration by parts involved here. It's a really simple question. It's L over n pi, and then sine integrates to negative cosine n pi over Lx. L cancels, and you still have to plug in L and L over 2 as the endpoints. So that gives you negative 2 over n pi cosine n pi over Lx, and you plug in L and L over 2. And that gives you negative 2 over n pi of cosine of, when L is plugged in, L and L cancels, you get cosine n pi, right? And then when you plug in L over 2, you have to subtract it. So be sure to put parentheses here because there's some confusion with the signs, right? So really think of this like that, okay? All right. So when you plug in L over 2, you get cosine n pi over 2 because L and L cancels, but you still have a 2 in the denominator. And we also know that cosine n pi is negative 1 to the nth power, so you can rewrite this as negative 1 to the nth power. But that's about it. That's the solution. All right, so we got the an, so we're halfway done. Now how do we tackle the problem of finding bn? Well, notice that this one single condition was enough to figure out what an is, so it must be that this second one should give you bn. So how do we use that? Well, because the left side of this condition has u differentiated by t, we better take this and differentiate by t. So if I differentiate this by t, you end up with cosine differentiates to negative sine, and by the chain rule this comes in front, so you get an times n pi a over L sine n pi a over LT. I'll just put t upstairs, it's the same thing, okay? And then plus bn. Differentiating sine gives you cosine, but again, because of the chain rule, n pi a over L will come up front. And then you get cosine n pi a t over L. And this entire thing gets multiplied by sine n pi over Lx. And notice that here I don't differentiate because this is a function in x. So in partial derivatives, this is considered as a constant. You only differentiate this one, okay? All right, so now you plug in t equals to 0. So what does that give us? The derivative of u with respect to t when evaluated at t equals to 0. That's like plugging in 0 into t here and there, and again you get sine 0, which doesn't give you anything at all, and here cosine 0 is 1, so you just end up with bn only, which is exactly what we want, right? So we want bn times n pi a over L times cosine 0 is 1, so we don't need that, and then sine n pi over L x. Okay, so this time what we end up with is another sine series. It's again the sine series, but here's a catch. See, we had the bn as the formula 2 over L integral of 0 to L of f of x sine n pi over Lx. However, this in turn expresses f of x as summation of bn sine n pi over Lx. So if you compare this with what we're trying to do over here, notice that this is really this one here, x L minus x. So this is our f of x in this formula. That's what we're going to do. But then here we just have bn, whereas here we have this much. So setting these two equal, what you end up with is saying that bn is capital Bn times n pi a over L, so that our bn, the capital Bn, would be L over n pi a, because you're dividing by this to this side and then multiplying by L to this other side. You end up with L over n pi a, the reciprocal, times Bn. So that's what you have to compute, right? For this function. All right, so let's erase the stuff and then we'll carry on the calculation. So Bn is n pi a over L times lowercase bn, but lowercase bn has the formula 2 over L integral from 0 to L. Oh, sorry, I realized that I should have taken the reciprocal of this. So let me erase this, put the reciprocal. It should be L over n pi a times 2 over L, 0 to L, x times L minus x sine n pi over Lx dx. So that's what you have to do. And then you can cancel these two and just simplify this as 2 over n pi a. So here's what we need. 2 over n pi a of integral from 0 to L of, well, I can multiply this out, right? So it's x times L minus x squared. And then sine n pi over L x dx. And then because this is a product of two functions, now we need the tabular integration. So let's do the, or integrate by parts, whichever you like. Okay, so plus or minus d integral, you put x L minus x squared, differentiate, you get L minus 2x, differentiate again, it's negative 2. And then over here, and then you differentiate again at 0. Okay, you have to until you get 0. And then here you have sine of n pi over L x, and every time you integrate, this n pi over L is reciprocal will come up front, so it's L over n pi. Actually, there's a minus cosine n pi over Lx. Integrating again, you get negative L squared, n squared pi squared, sine n pi over Lx. And then integrating again, you get positive L squared, n squared, sorry, this should be n cubed pi cubed, this should be cubed. And then cosine n pi over Lx. And there's a plus, minus, and then if you do like that, go like this, go like this, you can read off the integral as 2 over n pi a. And then it will be, let's see, x times L minus x. Let's rewrite xl minus x squared as x times L minus x, and you'll see the reason why a little bit later, okay? And it's times negative L over n pi cosine n pi over Lx. And then there's a minus times minus is plus, so let's put plus L minus 2x times L squared. I already took care of the minus, so this time it's only L squared, n squared pi squared sine n pi over Lx. And then finally it's negative 2 times L cubed over n cubed pi cubed cosine n pi over Lx. And then you have to plug in the L and 0. And here's the interesting part. If you plug in L into here, then L minus L gives you 0, right? So you don't get anything when you plug in L. Also, if you plug in L in here, you get L and L cancels, and you get sine n pi, which gives you 0. So you can see that when you plug in L, the only thing that gives you a non-trivial answer is when L is plugged in here and you get cosine n pi. So that's what you get when you plug in L. It's 2 over n pi a. The first two terms are 0, and you get negative 2 L cubed, n cubed pi cubed, and you get cosine n pi, which is negative 1 to the nth power. Okay, and then minus, let's plug in 0. When you plug in 0, when you plug in 0 into x, well, there's a 0 here, so that's going to go away. It'll be 0. And when you plug in 0 here, sine 0 is 0. So again, the first two terms don't produce anything. And the only non-trivial thing that's produced is when you plug in 0 here. So that gives you minus of negative 2L cubed over N cubed pi cubed. And the result is that you get cosine of 0, which is just 1. So that's it. And if you simplify this, you can further simplify by, say, minus minus is plus. And you can pull out the L cubed, N cubed, pi cubed, and 2 as a common factor. But there's also 2 there, so times 2 over N pi A. And then when that's done, you really have negative 1 to the nth power plus 1 here. And you can rewrite this as like 4L cubed over N to the 4th, pi to the 4th times A if you want. Yeah, so the fully simplified one will be 4L cubed over N to the 4th, pi to the 4th A. And then I can switch these around and say 1 minus negative 1 to the nth power. So that's it. That's the answer. So we found AN, we found BN. You use those values, and that gives you a solution that satisfies everything you see here.